What if James Webb didn't just photograph the universe? It accidentally found evidence of a different one. 2/3 of all galaxies in a key deep field are spinning the exact same direction. In a random universe that is mathematically impossible, a cosmos that should have no memory, no preference, no direction, is rotating like something set it in motion from outside. Then Webb found ancient galaxies fully built where nothing should exist. Then the universe gave two completely different answers for its own expansion rate, as if two different realities are overlapping. These are not minor glitches. These are cracks in the foundation of modern physics. And the deeper Webb looks, the worse it gets. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. For 100 years, we built a map, not a map of streets or coastlines, a map of time itself, a detailed, mathematically precise portrait of how the universe began, how it grew, and how the first stars and galaxies slowly assembled from the primordial dark. Physicists and astronomers spent generations constructing it, testing it, refining it, and by the early 21st century they were confident the map was nearly complete. Then we built a telescope powerful enough to actually look. And what the James Webb Space Telescope sent back, beginning in the summer of 2022, did not match the map. Not slightly. Not in one or two places. The mismatches appeared everywhere Webb looked, stacking one on top of another, each one stranger than the last. And now, several years into its operation, the scientific community is confronting a question that would have seemed almost unthinkable a decade ago. What if the map was wrong? Let's be precise about what we mean by the map. For the last several decades, cosmology has operated on a framework called the Lambda CDM model. That name is a mouthful, so let's break it down simply. Lambda refers to dark energy, the invisible force believed to be driving the universe's expansion. CDM stands for cold, dark matter, the unseen scaffolding thought to hold galaxies together. Together, these two invisible ingredients, combined with everything we can actually see, form the standard recipe for the entire universe. Think of it this way. Imagine you are baking a cake, but roughly 95% of the ingredients are invisible to you. You cannot see them, taste them, or touch them. You can only infer they exist because the cake holds together. That is essentially the situation modern cosmology is in. 95% of the universe, by current best estimates, is composed of things we cannot directly observe. Dark matter and dark energy are not metaphors. They are placeholders for forces and substances we have not yet identified. And yet, built on those invisible foundations, the Lambda CDM model made extraordinarily precise predictions. It told us how fast the universe should expand. It told us when the first stars should ignite. Most importantly, for what we are about to discuss, it told us exactly what the early universe should look like. Faint, primitive, chaotic. Small, irregular clumps of gas and dust, barely beginning the long, slow process of collapsing into galaxies. That is what the map said. Webb looked at the early universe, and the early universe looked nothing like that. The telescope was engineered to see in infrared light, a wavelength invisible to human eyes, but one that carries the ancient light of the most distant galaxies, light so stretched by billions of years of cosmic expansion that it has shifted far beyond what our eyes could ever detect. By observing in infrared, Webb could effectively look back in time, seeing the universe not as it is today, but as it was in its first few 100 million years of existence. What astronomers expected to find in those earliest epochs was a universe still in its infancy. Dim, disorganized, tentative. What they found instead were giants. Within the first weeks of scientific operations, Webb began detecting galaxies that had no right to exist at the time they were seen. Massive, luminous, structurally developed galaxies, some containing hundreds of billions of stars, appearing as early as 500 million years after the Big Bang. 500 million years sounds like a long time in human terms. A person living 500 million years ago would have found Earth almost unrecognizable. The first land-based plants had not even appeared yet, but in cosmic terms, 500 million years after the Big Bang represents barely 4% of the universe's current age. That is like expecting a newborn child and instead finding a fully grown adult standing in the delivery room. And it was not just their size. These galaxies were chemically complex in ways that should have required far more time to develop. Galaxies are forged by generations of stars, each generation born, living, dying in supernova explosions, seeding space with heavier elements, enriching the raw material for the next generation. Carbon, oxygen, iron, the elements that build planets and eventually living things, require multiple stellar generations to accumulate. Webb found them present far too early, as if the universe had somehow skipped entire chapters of its own development. Some of these early galaxies were not even shapeless blobs of gas, which is what the models predicted for such an early era. Several already showed organized spiral structure, the graceful pinwheel arrangement of arms that we associate with mature, settled galaxies like our own Milky Way. Cosmology had assumed that spiral structure required billions of years of gravitational settling to emerge. Webb found it appearing in what should have been the universe's most turbulent, unstructured period. Each individual discovery on its own might have been explained away. Perhaps a measurement error, perhaps an unusual local condition. Scientists are rightly cautious about single outliers, but the outliers kept coming. Then astronomers began noticing something in the galaxy rotation data that was harder to dismiss. In an unbiased, structureless universe, which is exactly what standard cosmology predicts on the larger scales, galaxies should spin in random directions, some clockwise, some counterclockwise, with no preferred orientation across the sky. The universe, according to the model, has no handedness, no top or bottom, no preferred axis. Every direction is as valid as every other, and the spins of galaxies should reflect that randomness. The way a coin flipped 1,000 times will land roughly 500 heads and 500 tails. Physicist Leo Shamir at Kansas State University analyzed galaxies from Webb's deep field surveys, among the most detailed images of the distant universe ever captured, and counted the spin directions of hundreds of identifiable spiral galaxies. What emerged from that count was not a 50-50 split. Roughly 2/3 of the galaxies rotated one way. Only 1/3 rotated the other. That is not a coin landing on heads 600 times out of 1,000. That is closer to 660 out of 1,000. In statistical terms, in a domain where scientists demand extraordinary precision, that asymmetry is deeply uncomfortable, and it was not a single anomaly from a single image. Multiple verification methods were applied, checking for instrumental bias, checking for classification errors, checking for the distorting effect of the Milky Way's own motion. The asymmetry survived all of them. The universe suddenly looked less random than anyone had assumed, and that had enormous implications we will follow closely, because a universe with a preferred spin direction is a universe with a memory, a universe that remembers something from before we can currently see. At the same time, these galaxy discoveries were accumulating a separate crisis, one that had been simmering for years before Webb launched, refused to go away. Cosmologists measure the expansion rate of the universe using a value called the Hubble constant. Think of it as the universe's speedometer, a single number expressing how fast space itself is stretching apart in every direction simultaneously. Measure it accurately, and you can reconstruct the entire history and future of the cosmos. The problem is that the universe gives two different answers, depending on how you measure it. When astronomers analyze the cosmic microwave background, the faint glow of radiation left over from the universe's earliest moments, essentially a photograph of the cosmos as an infant, they calculate an expansion rate of approximately 67 kilometers per second per megaparsec. A megaparsec is a unit of cosmic distance equal to roughly 3.3 million light-years, meaning for every such unit of distance, space is stretching apart at 67 kilometers per second. To put that in human terms, if two galaxies were separated by the distance light travels in 3.3 million years, they would be moving apart at around 42 miles every single second. But when astronomers use local methods, measuring the distances to nearby galaxies using pulsating stars called Cepheid variables and exploding stars called Type 1a supernovae, they consistently get a higher number, around 73 kilometers per second per megaparsec. That is roughly 45 miles per second across the same distance. The gap between 67 and 73 may sound small, but in cosmology, it represents a fracture. If the two values are both correct, then something fundamental is missing from the model. Either the early universe and the modern universe are governed by slightly different physics, which our current framework cannot explain, or both measurements are somehow wrong in ways that have gone undetected for decades. Before Webb launched, some hoped the discrepancy was simply a measurement error. Webb was designed in part to settle the question. Its infrared vision could peer through the dust clouds that had always complicated Cepheid measurements from earlier telescopes like Hubble. Astronomer Adam Rees and his team used Webb's improved precision to remeasure Cepheid stars in nearby galaxies with far greater accuracy than had ever been possible before. The local expansion rate came back at 73 again. The gap did not close. Webb confirmed it, and by confirming it, eliminated one of the simplest explanations cosmologists had been holding on to. And then there were the objects no one had a name for. Scattered throughout Webb's deep field surveys, those extraordinarily long exposures that collect light from the most remote corners of the observable universe, appeared small, intensely red, compact objects that did not fit any existing category. Astronomers began calling them little red dots. That name is informal, but the objects themselves are anything but. Most of these objects existed between 600 million and 1.5 billion years after the Big Bang, a period when, according to standard models, the universe should still have been dominated by relatively simple young structures. These objects were not simple. Their spectra, the breakdown of their light into different wavelengths, which acts like a fingerprint revealing their composition and physics, showed signatures associated with extremely energetic environments. Some showed gas moving at extraordinary velocities near their cores. Several appeared to conceal objects at their centers that, if the measurements are correct, would qualify as supermassive black holes containing millions or even billions of times the mass of our Sun. That, on its own, is not remarkable. Most large galaxies appear to harbour supermassive black holes at their centres, including our own Milky Way. What is remarkable is when these objects apparently existed. Standard astrophysical theory requires enormous amounts of time for a black hole to accumulate that much mass. A black hole grows by consuming surrounding material, and that process has limits, physical limits on how fast matter can fall in and how much energy gets released. Growing a black hole to billions of solar masses in just a few 100 million years would require that process to run at efficiencies our models say are physically impossible. Some physicists began revisiting an older, largely dormant idea that some black holes did not form from collapsing stars at all, that they formed directly from massive clouds of primordial gas in the universe's very first moments, or even from density fluctuations in the earliest instants after the Big Bang itself. Primordial black holes, they are called. The concept had existed in theoretical physics for decades, but had never found compelling observational support. Webb's little red dots gave the idea new life. Here is the moment that shifted the conversation. Each of these discoveries, the oversized ancient galaxies, the early spiral structures, the chemical complexity, the spinning asymmetry, the persistent expansion rate disagreement, the little red dots, could theoretically, in isolation, have a conventional explanation, an unusual measurement, a rare coincidence, a gap in our simulations. Scientists work with anomalies all the time. Anomalies are part of the process, but anomalies are supposed to be random. They are supposed to scatter in different directions, pointing at different errors in different parts of the model. What began disturbing cosmologists was not the existence of any single anomaly. What disturbed them was that several of these anomalies appeared to be pointing in the same direction. The galaxy spin asymmetry suggests the universe may contain a large-scale directional structure, a preferred axis built into the fabric of space itself. The expansion rate discrepancy suggests the early universe and the modern universe may not be evolving the same way, that something changed, or that something has always been present that the model never accounted for. The impossibly massive early galaxies and black holes suggest that structure formed faster than any known physical process allows. What if these were not separate problems? What if they were symptoms? Cosmologists began using a phrase in their papers and public discussions that they had rarely needed before. Missing ingredients. Not missing data, not missing measurements. Missing ingredients. Fundamental physical components or forces that the standard model simply does not contain, and without which the universe Webb is revealing cannot be explained. That phrase carries weight. Scientists do not use it lightly. Before Webb, cosmology felt, to many of its practitioners, close to finished. Not completely finished, no scientist would say that, but nearly assembled. The broad strokes were understood. The lambda CDM model matched observation after observation. The remaining gaps felt like details, not chasms. Webb did not add details. Webb revealed chasms. What is important to hold on to is this: Webb did not break science. Science does not break. What it does, when it encounters a sufficiently powerful observation, is what it has always done. It investigates, it questions, it rebuilds. The history of physics is a history of maps being replaced by better maps, each one more accurate, each one revealing that the territory was stranger and richer than anyone had imagined. Newton's map was replaced by Einstein's. Einstein's map is now being challenged not by failure, but by precision, by a telescope so accurate it can see the places where the model quietly does not hold. That is not a crisis of science. That is science doing exactly what science does. But what the map looks like on the other side of this, what the new ingredients are, what they mean, whether our most fundamental assumptions about the structure and origin of the universe need to be revised, remains genuinely, deeply unknown. And here is the thread that refuses to let go. Of all the anomalies Webb has delivered, one carries implications that extend furthest, not just into astrophysics, but into the very architecture of the cosmos itself. The galaxy spin asymmetry. 2/3 of the galaxies in the deep field surveys rotating one direction, 1/3 rotating the other. A universe that appears, against all expectation, to have a preferred orientation. In cosmology, that should be impossible. The standard model is built on the assumption that the universe looks the same in every direction, that there is no preferred axis, no favored angle, no handedness baked into space. That assumption is not decorative. Pull it out, and the foundations of modern cosmology begin to shift. So the question that now demands an answer is not simply why those galaxies spin the way they do. The question is what kind of universe could produce that pattern? What kind of universe is structured enough, organized enough, oriented enough to leave a statistical fingerprint across hundreds of billions of light years of space? Because there is one possibility, long abandoned, long dismissed, that has quietly returned to the conversation. The universe itself may be rotating. A rotating universe. Even saying it feels strange. We are accustomed to things inside the universe rotating. Planets, stars, galaxies, the great spiraling arms of nebulae. Rotation is everywhere we look. But the universe itself, rotating as a whole, the way a top spins on a table, that idea belongs to a category of thought that most physicists had long ago filed away as a historical curiosity. Interesting in theory, incompatible with everything we observe. Except the observation that prompted this question did not come from a theorist. It came from the data, from Webb's own images of the deep universe, and the closer you look at what the data actually shows, the harder it becomes to dismiss. To understand why this matters as much as it does, we need to sit with one of the quietest and most important assumptions in all of science. Modern cosmology rests on what physicists call the cosmological principle. Think of it as the great equalizer. The cosmological principle states that on the largest scales, when you zoom out far enough that individual galaxies become mere specks, the universe looks the same in every direction and from every location. No center, no edge, no preferred axis, no special direction, just a vast, even, structureless ocean of matter and energy, statistically identical no matter which way you face. This assumption is not decorative. Virtually every calculation in modern cosmology depends on it. The equations that describe the Big Bang, that predict how galaxies should form and grow, that model the expansion of space, all of them are built on the premise that the universe has no orientation. Remove that premise, and the mathematical foundations of cosmology do not simply need patching, they need to be rethought from the ground up. One of the cleanest tests of this principle involves galaxy rotation. Spiral galaxies, those beautiful pinwheel structures like our own Milky Way, rotate. Some spin clockwise when seen from a certain vantage point. Others spin counterclockwise. In a universe with no preferred direction, those two populations should be approximately equal across any large sample. The universe has no reason to favor one-handedness over the other, the same way a river on a perfectly flat, featureless plain has no reason to curve left rather than right. That equality, that statistical 50-50 balance, is what astronomers expected to find when they turned Webb toward the deep universe and began cataloging galaxies. It is not what they found. Physicist Lior Shamir at Kansas State University examined spiral galaxies detected within Webb's JADE survey, the JWST Advanced Deep Extragalactic Survey, one of the most detailed systematic studies of the early universe ever attempted. From that survey, his team identified 263 galaxies with spin directions clear enough to classify reliably. 263 galaxies spread across some of the deepest, most ancient reaches of space Webb has yet observed. In a cosmologically unbiased universe, you would expect roughly half to spin one way and half to spin the other. Perhaps 130 clockwise, 133 counterclockwise, a difference of a handful, attributable to random chance the same way a fair coin, flipped 263 times, might land slightly more on heads than tails in any given run. The actual count came back at 158 clockwise and 105 counterclockwise. That is not a coin landing slightly skewed, that is a gap of 53 galaxies. In a sample this size, under a truly isotropic universe, a gap that large has a vanishingly small probability of occurring by chance alone. The imbalance was not subtle. When Shamir's team looked at the Webb images directly, the asymmetry was visible, not hidden in abstract statistics, but present in the actual appearance of the galaxies themselves, arranged across the sky in a pattern that quietly defied what the standard model said should be there. But here is the thing that made this truly uncomfortable. Scientists do not trust single results. That is not a weakness of science. It is its most important strength. So before anyone raised an alarm, Shamir's team and other researchers subjected the spin asymmetry to a battery of tests designed specifically to find the error. Could the asymmetry be an artifact of how the telescope was pointed? Checked. Could it be a bias in how the classification software assigned clockwise versus counterclockwise labels? Checked. Could the Milky Way's own motion through space, a real measurable drift through the local universe, be Doppler shifting the light from distant galaxies in a way that mimicked a spin preference? Checked carefully, with independent mathematical corrections applied. The asymmetry survived every test, not weakened, not explained away, survived. Across several independent verification approaches, the signal held, and then researchers looked back at older data, observations from the Hubble Space Telescope collected years before Webb launched, and found that earlier surveys had hinted at the same directional asymmetry, a quieter signal, in smaller samples, pointing in the same general direction. It had been there all along. Hubble had whispered it. Webb shouted it. This raised a question that the data now demanded be taken seriously. What direction? Because if galaxies across billions of light-years of space are statistically more likely to spin one way than the other, and if that asymmetry is real rather than artifactual, then they are not spinning randomly. They are spinning in relation to something structural, something embedded in the architecture of the cosmos itself. And that is where the story became genuinely strange. Long before Webb launched, cosmologists had already been quietly troubled by a different anomaly, pointing to the same unsettling possibility. In the early 2000s, NASA's Wilkinson Microwave Anisotropy Probe, known as WMAP, produced the most detailed map ever made of the cosmic microwave background. The cosmic microwave background is the faint afterglow of heat left over from the Big Bang, radiation that has been traveling through space for nearly 13.8 billion years, carrying in its patterns a snapshot of the infant universe. Studying its irregularities tells us how matter was distributed in the earliest moments of cosmic history. In a truly isotropic universe, the patterns in that ancient radiation should be randomly distributed across the sky. No preferred direction, no special alignment, just statistical noise. But the WMAP data showed something unexpected. Certain large-scale patterns in the cosmic microwave background, specifically the largest fluctuations, the ones that should span the widest angles across the sky, appeared aligned. Not randomly scattered, aligned, as if pointing along a particular axis through space. Cosmologists Kate Land and João Magejo at Imperial College London analysed this alignment in 2005 and gave it a name that has stuck: the axis of evil. Not out of drama, but out of scientific frustration, because its existence violated the cosmological principle as directly as anything they had ever seen. A preferred axis in the microwave background meant a preferred direction in the universe's earliest observable imprint. That should be impossible. For years, many researchers attributed it to contamination, foreground emission from our own galaxy, obscuring the true background signal. But the alignment persisted as measurement methods improved, and when the European Space Agency's Planck satellite produced an even more precise microwave background map in 2013, the anomaly remained. The axis of evil did not go away, and then there was the dark flow. In 2008, astronomer Alexander Kashlinsky and his team at NASA's Goddard Space Flight Center published a remarkable and deeply controversial result. By analyzing the subtle imprint that galaxy clusters leave on the cosmic microwave background, a distortion caused by the cluster's motion, Kashlinsky's team found evidence that enormous numbers of galaxy clusters across vast regions of space appeared to be moving together in the same direction, not toward any visible gravitational source, not explained by any known structure in the observable universe, just drifting, collectively, toward a particular point on the sky, as if pulled by something enormous lying beyond the edge of what we can see. He called it dark flow. The name captures the mystery precisely: a large-scale motion with no identifiable cause within our visible cosmos. Dark flow remains scientifically contested. Other research groups have disputed its significance, and the debate has not been resolved. But here is what is difficult to ignore. The direction Kashlinsky identified for this mysterious bulk motion aligned, at least approximately, with the direction of the axis of evil anomaly in the microwave background. Now Shamir's galaxy spin asymmetry points roughly toward the same region of the sky. 3 independent anomalies, 3 separate measurement techniques, 3 different physical phenomena: galaxy rotation, microwave background patterns, large-scale cluster motion, all whispering about the same direction in space. That is not a coincidence that statistics can comfortably absorb. Here is where the contradiction becomes genuinely irresolvable with the tools we currently have. The cosmological principle states that no direction in the universe is special. That is not a preference. It is a mathematical necessity built into every equation we use to model the cosmos. Our entire understanding of the Big Bang, of cosmic expansion, of galaxy formation, all of it assumes this principle is true, at least to a very close approximation. But if the spin asymmetry is real, if the axis of evil is real, if dark flow is real, and if all three point toward a structure embedded in the large-scale fabric of space itself, then the cosmological principle is not approximately true. It is wrong, and the degree to which it is wrong is not a rounding error. A preferred axis that spans the entire observable universe, that leaves its fingerprint on galaxy rotations across billions of light years, is not a local fluctuation that can be averaged away. It is a feature the standard model has no mechanism to produce. The map says the territory is flat in every direction. The territory keeps pointing at one specific mountain on the horizon. Two explanations have emerged in the scientific literature, neither proven, neither eliminated, and the tension between them is exactly where the science currently lives. The first explanation involves what some physicists call primordial cosmic handedness. The idea is this: in the earliest instance after the Big Bang, the universe may not have expanded perfectly symmetrically. Some models suggest tiny rotational asymmetries could have been present from the very beginning, baked into the conditions of the infant cosmos before a single star or galaxy existed. As galaxies formed over billions of years, condensing out of this primordially biased medium, they would have inherited that handedness the way a river inherits the tilt of the land it flows across. The universe in this picture carries a memory, a directional signature from conditions so early and so extreme that we have no direct way to observe them. The second explanation is more radical and more ancient. Some physicists propose that the universe is not merely biased in one direction, but actually rotating, slowly, imperceptibly, on a time scale and a scale so vast that no single observatory could detect the motion directly. Only its statistical fingerprint, accumulated across thousands of galaxies, would reveal it. This idea is not new. Albert Einstein's own field equations, the mathematical framework that describes how matter and energy shape the geometry of spacetime, mathematically allow for rotating universe solutions. The mathematician Kurt Gödel explored them in detail in the 1940s and showed that such solutions were internally consistent. What they required was uncomfortable: a universe with a preferred axis, preferred directions, and, in some extreme formulations, the theoretical possibility of closed loops in time. Gödel's rotating universe was never disproven. Modern cosmology simply chose not to pursue it, because the observational evidence at the time gave no reason to. Webb may now be providing that reason. Critics of both explanations remain, and rightly so. The sample of 263 galaxies, while statistically striking, is not yet large enough to eliminate all alternative explanations with certainty. The Milky Way's peculiar motion through space, our local drift through the cosmos, independent of cosmic expansion, could in principle introduce Doppler effects that mimic a spin preference. This explanation has been tested and found insufficient to account for the full asymmetry, but the debate continues, and careful scientists hold their conclusions accordingly. The asymmetry may be real, or it may be a subtle systematic error that has so far resisted correction. What is not in doubt is the seriousness with which the cosmological community is now treating it. Something needs to be said clearly before moving forward. If the universe truly possesses a preferred axis, if galaxy spins really are biased across cosmic scales, and if this signal connects to the axis of evil and to dark flow, then the question that immediately follows is not simply what caused it. The question is something far deeper, something that pulls at the very foundations of how we think about the cosmos. A rotating universe, by definition, rotates relative to something. A spinning top rotates relative to the floor beneath it, the air around it, the gravitational field of the Earth. Take away all external reference points, and the concept of rotation loses its meaning. If the universe is everything, If there is nothing outside it, then what could it possibly be rotating relative to? There is only one class of answers to that question that does not collapse under its own logic, and those answers require the universe we inhabit to be not the whole of reality, but a region within something larger, a structure embedded inside a greater context, a bubble perhaps inside an ocean we have never seen. And if that is true, if our universe is not all there is but one of many, then the question of where it came from becomes something far stranger than any Big Bang model has ever dared to contemplate. The universe rotating relative to something, that is the idea we are now standing in front of. And it is worth pausing here for a moment, not to retreat from it, but to really feel how strange it is, because rotation in every context we have ever encountered requires a reference. A wheel rotates relative to its axle. The Earth rotates relative to the stars. Even a spinning top, if you remove the floor and the air and everything around it, loses the very meaning of its motion. Rotation is always a relationship, always defined against something external. So when physicists seriously entertain the idea that the universe itself might be rotating, they are not simply describing a curious motion. They are raising a question that cuts to the very foundation of what the universe is, and whether it is all there is. That question did not begin with Webb. It began with a man sitting across a table from Albert Einstein in Princeton in 1949. Kurt Gödel was not an astrophysicist. He was a mathematician, one of the greatest logicians of the 20th century, the man who proved in 1931 that any sufficiently complex mathematical system contains true statements that the system itself cannot prove. His incompleteness theorems shook the foundations of mathematics. They demonstrated, with quiet and devastating precision, that no formal system can be complete and consistent at the same time. Gödel and Einstein were colleagues and close friends at the Institute for Advanced Study in Princeton. They walked together daily. They talked about physics and philosophy and the nature of time, and in 1949, as a gift for Einstein's 70th birthday, Gödel offered something that no one expected: a new exact solution to Einstein's own field equations, the mathematical framework that describes how matter and energy curve the geometry of space-time itself. Gödel's solution described a universe that rotated, not a galaxy, not a cluster, not a region, the entire universe, rotating as a whole. And the extraordinary thing was this: the mathematics was valid. Gödel had not made an error. He had not stretched Einstein's equations beyond their limits. He had simply applied them to a new set of initial conditions, a universe filled with uniformly distributed matter, rotating at a constant angular rate, and the equations had accepted it. Within the framework Einstein had built, a rotating universe was not just conceivable, it was mathematically consistent. Einstein reportedly found this deeply unsettling, not because the math was wrong, but because it was right, and its implications extended far beyond mere rotation. To understand why Gödel's solution troubled Einstein so profoundly, we need to understand what rotation does to space-time. In Einstein's framework, matter and energy do not simply sit inside a passive, empty stage called space. They shape it, they curve it. A massive object, a star, a black hole, a planet, bends the geometry of the space and time around it, the same way a heavy ball placed on a stretched rubber sheet creates a depression that nearby objects slide toward. Space-time is not a fixed backdrop. It is a dynamic, flexible structure that responds to whatever inhabits it. Rotation adds a further layer to this. A rotating object does not merely curve the space-time around it, it drags it. Imagine stirring a spoon slowly through a thick liquid. The liquid near the spoon does not stay still. It gets pulled along, swirling in the same direction as the spoon's motion. A rotating, massive object does the same thing to space-time. It physically twists the geometry of space and time in the direction of its rotation. This effect has a name: frame dragging. Physicists have measured it directly using satellites in orbit around Earth, confirming that our planet's rotation does, in fact, subtly drag the space-time fabric around it. Now scale that up. A rotating universe would frame drag space-time everywhere. The geometry of space itself, the structure through which all light travels, the medium through which all motion occurs, would be twisted in the direction of the cosmic rotation, and that would leave marks on how light bends as it crosses the cosmos, marks on which directions feel subtly different from which other directions, marks potentially on which way galaxies tend to spin as they condense out of the rotating medium of primordial gas. That last point is what connects Gödel's 1949 mathematics to Webb's 2023 data. If the infant universe rotated, even very slightly, even by an amount far too small to detect through any direct observation, the galaxies that formed within it would carry that original handedness the way iron filings, scattered onto a magnetized surface, align themselves along invisible field lines. The galaxies would not be forced to spin one way, but they would be statistically biased. The spin they inherited from their environment would show up, very faintly, in the count, 2/3 one way, 1/3 the other. But rotation was only the beginning of what Gödel's solution contained. When you work through the complete mathematics of a rotating universe, when you follow what happens to the paths that particles and light can travel through such a geometry, you encounter something that stopped physicists cold. Gödel's rotating universe permitted what are called closed time-like curves. That phrase requires unpacking immediately. A time-like curve in physics is simply the path that any object with mass traces through space-time as it moves. You are on a time-like curve right now, moving forward through time, carried by the ordinary flow of events from past to present to future. In normal space-time, these paths are open. They never loop back. Time flows one direction, and no trajectory through space-time can bring a particle back to where and when it started. In Gödel's rotating universe, the geometry curves so severely that some of these paths close. They loop, a traveller following such a path, not by moving faster than light, but simply by travelling through space in a way that exploits the twisted geometry, could, in principle, return to their own past. Not as a science fiction device, as a mathematical consequence of valid physics. Einstein was disturbed by this, not because he thought a person could actually build a time machine in Gödel's universe, but because the existence of closed time-like curves within a valid solution to his own equations suggested that his framework might not fully capture the nature of time. Gödel himself believed this was intentional, that his solution revealed something deep and troubling about the relationship between physics and the experience of time passing. Time, Gödel argued, might be far less objective, far less real in a physical sense than our intuitions assume. Modern cosmology's response was, in effect, to set Gödel's solution aside, not to disprove it, not to find a flaw in the mathematics, but to note that the universe we actually observe does not appear to match the conditions Gödel described, and to move on. That decision now looks at minimum premature. For decades, the rotating universe lived in a quiet corner of theoretical physics, explored occasionally by mathematicians, referenced in textbooks as a technically valid but observationally unsupported possibility, and largely ignored by working cosmologists building the models that would become the lambda-CDM framework. A universe with no preferred direction was far simpler to work with, and simpler models, when they fit the data, tend to win. The data, for a long time, supported simplicity. The cosmic microwave background looked at the largest scales statistically uniform. Galaxy surveys showed no dramatic large-scale asymmetries. The cosmological principle, the assumption that no direction is preferred, held up well enough across observation after observation that questioning it began to feel like a theoretical indulgence rather than a scientific necessity. And then Webb turned on. The galaxy spin asymmetry that Lior Shamir's team extracted from Webb's deep field data did not prove Gödel right, but it did something almost as significant. It gave physicists observational permission to take the idea seriously again. Papers began appearing in peer-reviewed journals, not dismissing the rotating universe hypothesis as a curiosity, but treating it as a live candidate for explaining what Webb had found. Ideas that had been dormant for 70 years found themselves in active scientific discussion again, not because cosmologists had grown less rigorous, but because the data had grown more insistent. And here is the thing most people do not immediately appreciate. Reviving the rotating universe hypothesis does not require the universe to be spinning fast. Even an extraordinarily slow rotation, a rate so glacially small that no single observation across a human lifetime could detect the motion directly, would be sufficient over 13 billion years to bias galaxy formation in exactly the pattern Webb observed. The universe would not need to be obviously spinning. It would only need to have been very slightly, consistently, persistently biased in one direction since the very beginning. The signal would be subtle, quiet, spread across billions of light years, almost invisible, almost. And this is where the physics arrives at its most irresolvable point. If the universe rotates, it possesses angular momentum. Angular momentum is the physical quantity that describes the amount of rotation in a system, the property that makes a spinning gyroscope resist being tilted, and that makes a skater spin faster when she pulls in her arms. In any closed physical system, angular momentum is conserved. It does not spontaneously appear. It does not spontaneously vanish. If the universe is rotating today, it was rotating at the Big Bang. If it was rotating at the Big Bang, something must account for that original spin. But the universe, in the standard model, is everything. There is nothing outside it. No larger medium that could have imparted a torque, a twisting force, to set it spinning. In classical physics, rotation requires an external reference and an external push. A universe that contains all of space, all of time, all of matter and energy, has nothing external to push against, nothing external to define its rotation relative to, and nothing external to have started it moving. So the question stands, unanswered, at the center of this entire discussion. If the universe rotates, what is it rotating relative to? There's only one class of physical framework in which this question has a coherent answer. The universe would need to be embedded within something larger, a greater structure, a higher dimensional medium, a surrounding environment of some kind, relative to which the observable universe could spin the way a planet spins relative to the space around it. The universe would not be all there is. The universe would be a region within something we cannot currently see, cannot currently measure, and may never directly access. That something has a name that most physicists use with careful, deliberate caution: the multiverse. The word multiverse tends to conjure extravagant images, parallel worlds, alternate versions of history, an infinite cascade of universes identical to our own, except for small quantum differences. That version of the multiverse comes from certain interpretations of quantum mechanics, and its relationship to observation is complex and contested. The multiverse that a rotating universe requires is different in character, less exotic in some ways, more structural. The idea is not that infinite copies of our universe exist side by side, each slightly different. The idea is simply that our universe, the entire observable cosmos, all 13.8 billion light-years of it, may be one region within a larger physical framework. A bubble, perhaps, that inflated from a quantum fluctuation in some primordial medium that predates space and time as we know them. A daughter structure within a larger parent, the way a soap bubble forms within the air around it, rather than constituting all of reality itself. In this picture, the parent structure could have possessed its own properties, its own geometry, its own dynamics, perhaps its own rotation. And a universe born within such a structure, born from a region of it that carried angular momentum, would inherit that spin the way a river inherits the gradient of the land it flows across. The rotation of the observable universe would not be a property it generated internally. It would be a memory, an echo of conditions that existed before the Big Bang, in a domain we have no telescope powerful enough to see. This is not a claim that the multiverse exists. Science requires evidence, and the multiverse, by most current formulations, lies beyond the reach of any observation we know how to design. What it is instead is the logical consequence of taking the rotating universe hypothesis seriously. Follow the physics honestly, and it leads to a place where our universe must have an outside. The data has not yet confirmed that we are in that place, but it has, for the first time in a serious and quantitative way, pointed in that direction. Physicists working in this area are careful, and they should be. The galaxy spin asymmetry is real and statistically meaningful, but 263 galaxies, while striking, represent a small sample against the hundreds of billions of galaxies in the observable universe. Future deep field surveys, including additional data from Webb itself, from the Euclid Space Telescope launched by ESA in 2023, and from the Vera C. Rubin Observatory beginning its survey of the southern sky, will catalogue galaxies by the tens of millions. If the spin asymmetry is a real feature of the large-scale universe, that signal will grow sharper and more statistically decisive with each additional survey. If the asymmetry disappears into noise as the sample expands, then the simpler explanation, measurement bias, Milky Way motion, statistical fluctuation, will have won. Science does not rush this process. The data speaks at its own pace, but the conversation has changed. Cosmology has spent the last 70 years building models on the premise that the universe has no preferred direction, no angular momentum, no handedness, and getting extraordinary mileage out of that simplification. Now, for the first time, an instrument precise enough to test that premise at cosmic scale is finding evidence that the premise may not hold. Not broken, not certainly wrong, but strained in a way that demands attention rather than dismissal. Gödel offered Einstein a rotating universe as a birthday gift. Einstein found it disturbing. The gift, it seems, was not a curiosity. It was a warning that the map of the cosmos left something out, and that when the instruments finally became good enough to look, the territory might show it. The rotating universe, if real, carries one implication that extends further than any question of angular momentum or multiverse geometry. A universe that rotates is a universe that had a beginning shaped by something outside it. A universe that inherited its spin means a universe born from a parent, and a universe born from a parent raises the possibility, disturbing and extraordinary in equal measure, that the very conditions inside our cosmos were set, at least in part, by conditions we cannot see and may never access. But there is another way that question surfaces in the Webb data, a quieter, more immediate way, one that does not require rotation or preferred axes or multiverse frameworks to be unsettling, one that becomes clear when you simply look at the galaxies themselves, at how old they appear, how massive, how chemically complex, how structurally mature, and ask the question that the standard model cannot answer with any comfort. How did they grow so fast? That question sounds simple. It is not. Behind it sits one of the deepest challenges the standard model of cosmology has ever faced. Not a question about exotic physics or theoretical abstractions, but a question about something concrete and visible. Galaxies. Real, structured, chemically complex, fully assembled galaxies, captured in Webb's images, existing at a time when the universe was so young it should not have been capable of producing anything remotely like them. The rotating universe, the spin asymmetry, the axis of evil, those anomalies live at the edge of observational certainty, in the territory of statistical signals and contested interpretations. The early galaxy problem is different. Webb stared directly at these objects, measured their light, recorded their spectra. The question of how they got there is not a matter of statistical noise. The objects are real. The timeline is the problem. To understand why these early galaxies are so disturbing, we need to understand what cosmology actually predicts about how a galaxy comes to exist. The standard model describes galaxy formation as a long, slow, bottom-up process. Physicists call it hierarchical structure formation, meaning small things form first, and larger things assemble gradually from the merging and accumulation of smaller things over vast stretches of time. In the beginning, the universe was almost perfectly uniform, a nearly featureless fog of hydrogen and helium gas, with only the most subtle density variations rippling through it. Over hundreds of millions of years, gravity amplified those tiny variations. Slightly denser regions pulled in surrounding material. Gas collapsed. The first stars ignited, enormous, violent, short-lived objects that burned through their fuel in only a few million years and exploded in supernovae, seeding the surrounding space with the first heavy elements. Think of it as the universe slowly building a city from scratch. First, the raw land is cleared. Then individual bricks are fired. Then small structures rise. Then over generations, those smaller buildings are demolished and combined into larger ones, which are eventually incorporated into blocks, which assemble into neighborhoods, which eventually form a full city. The whole process is time-consuming, not because the workers are slow, but because the materials, the bricks themselves, have to be manufactured first from raw ingredients before any construction can begin. In this framework, a galaxy the size of the Milky Way, containing somewhere between 200 billion and 400 billion stars, spanning roughly 100,000 light-years across, should require several billion years to assemble. Multiple generations of stars need to live and die. Their supernova explosions need to enrich the surrounding gas with the heavy elements that allow subsequent generations to form differently. Dwarf galaxies need to merge. Halos of dark matter need to accumulate and deepen their gravitational wells. The whole construction is a process of patient accumulation. Webb found the city already standing, within the first few 100 million years after the Big Bang, a period representing barely 3 to 4% of the universe's current age of 13.8 billion years. Webb's instruments detected galaxies that should not have existed. Picture this in human terms. The universe is 13.8 billion years old. If you compress that entire history into a single calendar year, where the Big Bang occurred at midnight on January 1st, then 500 million years would correspond to roughly the middle of January, 13 days into the year, and Webb found fully assembled, massive, chemically complex galaxies already present at that moment, the equivalent of arriving in a city 13 days after its founding and finding not a construction site, but a complete skyline. Some of these galaxies rivaled the Milky Way in total stellar mass, accumulating hundreds of billions of solar masses of material in a window of time so narrow that our best simulations, when forced to reproduce it, required star formation rates so extreme they violated the physical limits built into the models themselves. Astronomers ran the simulations. They adjusted the parameters. They pushed the efficiencies as high as the physics would allow. The early galaxies still outpaced what the models could explain. And then Webb found Zhulong. Announced in 2025 by a team using Webb's deep imaging capabilities, Zhulong, named for a primordial dragon deity from Chinese mythology, stood out even among the other anomalous early galaxies as something genuinely remarkable. Existing roughly 1 billion years after the Big Bang, Zhulong displayed the structural characteristics of a mature spiral galaxy, the organized, rotating disk of stars and gas that we associate with settled, evolved systems like our own Milky Way. Its stellar mass placed it in the same league as the Milky Way itself. 1 billion years. That sounds like a long time, but the Milky Way is believed to have taken most of the universe's entire history, nearly 10 billion years of gradual assembly, to reach its current form. Zhulong accomplished something comparable in 1/10 of that time, or less. The comparison is stark. Imagine someone handed you the completed manuscript of a 1,000-page novel on the day the author first sat down to write. Not a draft, not a sketch. The finished work, fully edited, bound, and printed. Similarly, a galaxy called Alaknanda displayed clear signs of organized spiral structure during what cosmologists call cosmic dawn, the era immediately following the first stars, when the universe was barely emerging from its primordial darkness and beginning to form the first structured objects, organized spirals at cosmic dawn. The models had not predicted this. The models had, in fact, specifically predicted against it. But the structural maturity of these early galaxies was not the only problem. Their chemistry was equally disturbing. Every element heavier than hydrogen and helium, oxygen, carbon, iron, silicon, the building blocks of planets, and eventually of living things, originates inside stars. Stars forge these heavier elements through nuclear fusion in their cores, then disperse them across space when they die in supernova explosions. The next generation of stars forms from this enriched material, building on what the previous generation left behind. This process is generational. It takes time, lots of it, for a galaxy to contain significant quantities of heavy elements, for its stars to show the spectral signatures of enriched chemistry that Webb detected in several of these early systems. It must have already hosted multiple generations of stars, stars that formed, lived their lives, exploded, and seeded the galaxy with their processed material, all before the galaxy in question even appears in Webb's field of view. The heavy elements Webb detected in some of these ancient galaxies implied a star formation history that stretched back even further than the galaxies themselves seemed to allow. The universe had not merely produced these galaxies too fast, it had apparently run through multiple stellar generations before the moment Webb captured. Generations that, by the standard timeline, should not yet have had time to complete a single cycle. This created what cosmologists began describing as a missing time problem embedded inside the missing mass problem. Not just too much galaxy for the available time, too much stellar history for the available time to have contained. Scientists do not abandon frameworks without exhausting every alternative. The standard model has survived generations of observational challenges by finding ways to absorb anomalies, and several serious proposals emerged in response to the early galaxy discoveries. None of them, so far, has resolved the tension completely. The first proposal involves hidden black holes. Some researchers suggested that active supermassive black holes at the centers of these early galaxies might be enhancing their apparent brightness, making them appear more massive and more luminous than they actually are. A powerful central black hole, actively consuming surrounding material, can outshine an entire galaxy of stars, flooding a telescope's detector with light that mimics the signature of an enormous stellar population. If the apparent masses of these early galaxies were inflated by black hole luminosity, the discrepancy with the model might shrink. The problem is that when astronomers carefully separated the central black hole contribution from the surrounding stellar light, a technically demanding but achievable process, many of these galaxies remain too massive even after the adjustment. The hidden black hole. Explanation weakened the tension. It did not dissolve it. The second proposal involves the nature of the very first stars. The initial generation of stars, called population 3 stars, the first objects to form from the pristine hydrogen and helium of the early universe, may have been far more massive than any stars forming today. Some theoretical models suggest these primordial giants could have contained hundreds or even thousands of times the mass of our Sun. Stars that enormous burn extraordinarily fast and die in catastrophic explosions, enriching their surroundings with enormous quantities of heavy elements in a single violent event. If population 3 stars were systematically more massive than current models assume, the early universe could have accumulated heavy elements and stellar mass far more rapidly than standard timelines predict. This is a plausible idea, but population 3 stars have never been directly observed. They existed so early and burned so briefly that their light has long since faded beyond detection. The proposal remains theoretical, and the degree to which it could account for the full extent of what Webb observed remains genuinely uncertain. Dust corrections, the process of accounting for how clouds of cosmic dust absorb and re-emit light, altering a galaxy's apparent brightness and color, were applied systematically. They helped in some cases. They failed to resolve others. Webb detected excess infrared luminosity across multiple independent deep field surveys, in galaxies at various distances and in various environments, in a pattern consistent enough that instrument bias or local contamination became increasingly difficult to invoke as explanations. The candidate galaxies exceeded theoretical predictions not in one survey, not in two, but repeatedly across independent teams using independent analysis methods. Here is the point at which the tension becomes genuinely irresolvable within the standard framework. Galaxy formation is not merely a matter of having enough gas available. Stars form from gas clouds, but only when those clouds reach a critical density and temperature, and the process is inefficient by nature. In our current models, only a small fraction of the gas in any given region actually collapses into stars. The rest is dispersed by radiation pressure from the newly formed stars themselves, by supernova shockwaves, by the turbulence of gravitational dynamics. Current simulations suggest that in a typical galaxy-forming environment, somewhere between 1 and 10% of available gas actually ends up inside stars during any given episode of star formation. 1 to 10%. To explain the masses of the earliest Webb galaxies within the time available, the simulations required efficiencies closer to 100%. Every available gram of gas converted into stars, essentially no loss to dispersal, turbulence, or radiation pressure. The physics of star formation, as we currently understand it, does not permit this. The mechanisms that limit star formation, radiation feedback, supernova shockwaves, magnetic fields threading the gas clouds, do not simply switch off because the universe is young. They are fundamental physical processes, not historical accidents. The models were not slightly wrong, they were demanding the impossible. By 2023 and into 2024, something rare had begun happening in the cosmological community. Leading researchers were stating publicly in peer-reviewed papers and at major conferences that the standard model of galaxy formation appeared to contain a missing ingredient, not a missing measurement, not a missing calibration, a missing ingredient, some physical process, some mechanism, some component of the early universe that the lambda-CDM framework had never accounted for, and without which the galaxies Webb was finding could not be produced. Some researchers began cautiously exploring whether the universe itself might be older than the current consensus figure of 13.8 billion years, whether the age estimate needed revision in a way that would provide more time for structure to form. These proposals remain deeply contested, and the mainstream of cosmological opinion has not adopted them. The evidence for the current age of the universe, derived from multiple independent methods, remains robust, but the fact that such proposals are appearing in the peer-reviewed literature at all, being published, discussed, and debated rather than immediately dismissed, marks a significant shift in the intellectual temperature of the field. What Webb has established, beyond reasonable doubt, is that the early universe produced galaxies far more efficiently, far more rapidly, and far more structurally complete than the standard model predicted. That is not a claim made by a handful of outliers. It is the emerging consensus of the community that built the standard model and spent decades refining it. The map and the territory have diverged. The divergence is real, and the missing ingredient that would reconcile them has not yet been found. The early galaxy problem and the rotating universe hypothesis share something important, a quality that makes them, together, feel like more than the sum of their parts. Both point to a universe that formed too much structure, too fast, too organized, too oriented, as if the conditions that produced it were somehow richer, more constrained, more directional than a standard Big Bang expanding from a single point into featureless symmetry should ever have generated. A universe that randomly expands from a structureless beginning should produce structure slowly, randomly, symmetrically. No preferred axis, no chemical complexity in the first billion years, No fully assembled spirals before the cosmic construction site has even cleared its foundations. And yet, what if the conditions at the beginning were not random? What if the universe did not emerge from a point of perfect symmetry, but from something that already possessed structure? A parent event that imprinted not just energy into the newborn cosmos, but direction, organization, perhaps angular momentum itself. That idea has a name in modern physics, and the mechanism it proposes involves not stars, not galaxies, not rotating space-time, but objects so extreme, so dense, so total in their gravitational dominance that nothing, not light, not information, not any signal of any kind, has ever been known to escape them. Objects so extreme that nothing escapes them. That is where the evidence has quietly led us. Not by accident, and not through a single dramatic discovery, but through a chain of observations, each one stranger than the last, that keeps pointing toward the same uncomfortable conclusion. The galaxies that grew too fast, the black holes that appeared too early, too massive, too fully formed, the spin asymmetry that suggested the universe inherited something from its own origin conditions. Every thread, when pulled, seems to run toward the same dark territory. What if the universe did not begin from nothing? What if our entire cosmos, every galaxy, every star, every particle of matter across 13.8 billion light-years was born inside a black hole in some larger reality we will never be able to see? That is not a metaphor. That is a serious proposal in modern theoretical physics. And the strangest part is not that someone proposed it. The strangest part is that the mathematics, when examined carefully, does not forbid it. To understand the black hole universe hypothesis, we need to first be clear about what a black hole actually is, not as a cultural symbol, but as a physical structure. A black hole forms when an enormous amount of mass collapses into an extraordinarily small region of space. The gravity becomes so concentrated, so overwhelming, that it bends the geometry of space-time around it into a kind of one-way drain. At a certain boundary, called the event horizon, the curvature of space-time reaches a critical point. Past that boundary, every possible path through space-time, including the path of light itself, curves inward. Nothing that crosses the event horizon can return, not because of any barrier or wall, but because all roads, all directions, all futures curve toward the interior. Outward is no longer a direction that exists on the inside of an event horizon. Time and space effectively swap their roles. Think of it this way. Right now, you can choose to move left or right, forward or backward. You have spatial freedom in all directions, but you cannot choose to move backward in time. Time, for you, flows only one way. Inside an event horizon, the same inevitability that forces you forward through time forces everything inward through space. Escape is not difficult. Escape is geometrically impossible. At the very center of a black hole, according to the standard mathematical solution derived from Einstein's general relativity, the density becomes infinite. All the matter that collapsed reaches a single point of zero volume and infinite density, what physicists call a singularity. A singularity is not a physical object. It is a place where the equations break down entirely, where the laws of physics as we currently understand them cease to give meaningful answers. And here is the key insight that opens the door to everything that follows. A singularity, in physics, is almost always a sign not that something truly infinite exists in nature, but that the theory being used to describe it is incomplete. Einstein's general relativity, for all its extraordinary precision and predictive power, does not incorporate quantum mechanics, the framework that governs the behavior of matter at the smallest scales. At the densities inside a collapsing black hole, both theories become relevant simultaneously, and that combination has never been fully reconciled. One approach to addressing this gap involves a modification of Einstein's framework called Einstein-Cartan theory. Standard general relativity describes how mass and energy curve the fabric of space-time, bending it, stretching it, shaping it the way a heavy object shapes a stretched surface. Einstein-Cartan theory adds a second geometric property to spacetime called torsion. Torsion describes not the bending of spacetime, but its twisting, a rotational quality embedded in the geometry itself, distinct from curvature. Imagine the difference between bending a piece of paper into a curve and twisting it along its length like a spiral staircase. Both are geometric properties. Curvature and torsion are, in this sense, the two fundamental geometric qualities spacetime can possess. In standard general relativity, torsion is set to 0. It is simply ignored, not because it was proven absent, but because the mathematics is simpler without it, and the theory matched observations adequately. Einstein-Cartan theory retains it, and when torsion is retained, something remarkable happens inside a collapsing black hole. The spin of subatomic particles, the intrinsic rotational property that every fundamental particle carries as a basic physical characteristic, generates torsion in the spacetime around it. At ordinary densities, this effect is negligible, vanishingly small, but as matter collapses inside a black hole and the density rises toward the extreme values that approach a singularity, the torsion generated by the collective spin of all the particles becomes significant, and at a critical density, extraordinarily high but finite, the torsion generates a repulsive force, not an explosion, not a conventional pressure, a geometric repulsion built into the structure of spacetime itself. The collapse does not reach a singularity. Instead, the matter reaches the critical density, bounces, and rebounds outward, not back into the parent universe. The event horizon prevents that. Instead, the rebounding matter expands into a new region of spacetime that the collapse itself has created. A new, expanding region. A new universe, born inside the event horizon of the old one. From inside that new universe, the rebound looks indistinguishable from a Big Bang. The physicist who developed this framework most rigorously is Nikodem Popławski, working at the University of New Haven. Building on Einstein-Cartan theory and its treatment of torsion, Popławski published a series of papers beginning around 2010, arguing that every black hole may serve as the seed of a daughter universe, and that our own Big Bang may have been exactly such a rebound event, occurring inside a black hole belonging to some larger parent cosmos. The implications of this idea cascade quickly. If every collapsing black hole generates a daughter universe, and if every daughter universe eventually produces stars that collapse into black holes of their own, then the process is recursive. Each universe gives birth to more black holes. Each black hole potentially seeds another universe. Each of those universes generates more black holes indefinitely. The cosmos in this picture is not a single structure with a single origin. It is a branching, self-generating hierarchy of nested spacetimes, each one born from the gravitational collapse of matter in its parent, stretching backward and forward through a kind of meta-time that has no clean beginning or end. This was a version of an idea that physicist Lee Smolin had explored in a different theoretical framework in the 1990s, what he called cosmological natural selection. Smolin's proposal, however, was less specific about the mechanism. Popławski's work grounded the idea directly in Einstein-Cartan geometry and gave it a more concrete physical basis. Now, here is where the Webb data enters in a way that physicists did not initially expect. If our universe was born inside a rotating black hole, and the overwhelming majority of black holes in nature are rotating because the stars and gas clouds that collapse to form them carry angular momentum, then the rebound that became our Big Bang would have inherited that rotation. The daughter universe would spin in the same sense as the parent black hole. That spin would not manifest in some obvious, visually dramatic way. The universe we observe does not look like a spinning top, but it might, over billions of years of galaxy formation, as gas clouds collapsed along the rotational bias inherited from the birth event, produce a subtle statistical preference in which direction galaxies tend to spin. 2/3 one way, 1/3 the other. The match between what Popławski's framework loosely predicts and what Shamir's analysis of Webb's JADES data found is not a mathematical proof. The researchers themselves are careful about this. The theoretical prediction is qualitative, not quantitative. The framework predicts a spin asymmetry could exist, not what its precise magnitude should be. The observational signal is real, but based on a sample that future surveys must expand before it can be treated as definitive. But the correspondence exists, and it exists in a domain, the large-scale handedness of the observable universe, that the standard model predicts should not exist at all. The arrow of time also fits naturally into this framework, in a way that general relativity alone has always struggled to explain. The one-way nature of time, the fact that you remember the past and not the future, that eggs break but never spontaneously reassemble, that entropy increases in one direction, has always sat awkwardly inside physics, which at the fundamental particle level is largely time-symmetric. Why does time flow one way? In the black hole cosmology picture, the answer has a structural origin. The event horizon of the parent black hole is a one-way surface. Everything inside it is constrained to move in one direction, inward toward the interior. The daughter universe inherits this asymmetry. Time flows one way because the cosmos was born inside a boundary that permitted only one direction of travel. Whether this explanation is correct remains unknown, but it is, at minimum, structurally coherent in a way that other proposed explanations for time's arrow often are not. The black hole universe hypothesis remains speculative. This needs to be stated plainly and held alongside everything else. The absence of a singularity in Einstein-Cartan theory is a theoretical result. Physicists have not observed the interior of a collapsing black hole, and likely never will, given that the event horizon permanently seals any information inside. The daughter universe, if it exists, cannot send signals back to its parent. The parent universe cannot observe its daughters. The boundary between them is absolute, imposed by the geometry of the event horizon itself. This means the hypothesis faces a challenge that all multiverse frameworks face: the difficulty of generating predictions that could, even in principle, be tested. If our universe is sealed inside a black hole in a parent cosmos, no observation we can make from within our universe can directly detect the parent. The seal is perfect, and yet the spin asymmetry offers something that most multiverse proposals never provide: an indirect prediction about an observable quantity inside our own universe. If the hypothesis is correct, if our universe was born inside a rotating black hole and inherited its angular momentum, then large-scale surveys of galaxy spin directions should show a statistical preference. That preference should persist and likely grow clearer as the sample of surveyed galaxies expands from hundreds into the millions that future instruments will catalogue. That is a testable prediction. Not a certain one, not a precise one, but a real one. If ESA's Euclid telescope, or the Vera C. Rubin Observatory, or the next generation of deep field surveys finds no large-scale spin asymmetry in galaxy populations, the hypothesis loses one of its most compelling pieces of observational support. If the asymmetry strengthens and persists, it will not prove the black hole cosmology picture, but it will make that picture significantly harder to dismiss. Many cosmologists remain deeply skeptical, not because the mathematics is clearly wrong, but because the philosophical implications are so far-reaching that the scientific community appropriately demands extraordinary evidence before entertaining them as more than theoretical curiosities. That skepticism is healthy. That is how science is supposed to work. What has changed in the years since Webb's first deep field images arrived is that the category of ideas being taken seriously has quietly expanded. Proposals that would have been dismissed outright a decade ago are now appearing in peer-reviewed journals, being presented at major conferences, and being tested against real data. The Overton window of cosmological theory has shifted, not because the evidence has confirmed any single alternative, but because the standard model's anomalies have accumulated to the point where exploring alternatives has become scientifically necessary rather than merely philosophically interesting. There is one final implication of the black hole cosmology framework that is worth sitting with, not because it resolves anything, but because it reframes the entire question of cosmic origins in a way that feels genuinely new. If universes are born inside black holes, and if black holes form wherever sufficient mass collapses inside a universe, then the origin of any individual universe is not a mystery, independent of the universe that came before it. The Big Bang that created everything we can observe was not an event that came from nothing. It was a consequence of physics, the physics of a collapsing star, or a collapsing gas cloud in some parent cosmos whose own properties shaped the conditions of ours. Our universe in this picture did not begin, it continued. The physics that governed our origin was inherited from a structure that predated us. The constants of nature, the strength of gravity, the charge of the electron, the mass of the proton, might not be arbitrary. They might be the output of a physical process occurring in a domain we will never access, determined by conditions set before our space-time existed. That is a profound shift, not in what we can observe, but in what we are asking. The question is no longer simply, why did our universe begin? The question becomes, what kind of universe was capable of producing ours? And here is the thing that connects this idea back to everything we have observed. Whether or not the black hole cosmology framework is correct, whether or not our Big Bang was a rebound inside someone else's event horizon, the evidence Webb has delivered consistently points to a universe that arrived with more structure, more organization, more directionality than a standard, structureless beginning should have produced. The rotating universe, the oversized ancient galaxies, the galaxy spin asymmetry, the early black holes that were impossibly massive. Each anomaly on its own might be explained away. Together, they form a pattern, and the pattern suggests a universe that remembers something. But there is another anomaly that has nothing to do with galaxy spins or ancient black holes, an anomaly that was discovered not by Webb, but by the most precise measurements of the universe's expansion rate ever made, an anomaly that survived every attempt to explain it away, including the corrections Webb itself was specifically designed to provide, an anomaly about the speed at which the universe is expanding, and why it refuses to give the same answer twice. That is not a poetic way of describing uncertainty. That is a precise description of what happens when scientists measure the single most fundamental property of the cosmos, the rate at which all of space is expanding, using two different, completely independent methods. Both methods are rigorous. Both have been refined over decades. Both are grounded in physics that has been tested thousands of times in thousands of contexts. And they disagree, significantly, stubbornly, in a way that has survived every attempt to make it go away. This discrepancy had been building for years before Webb launched. Many researchers hoped Webb would resolve it. They expected that Webb's extraordinary precision would expose a subtle measurement error somewhere in the chain, a miscalibrated standard, a poorly corrected dust absorption, a crowded field of stars confusing the analysis. Webb was pointed at the problem with exactly that expectation. Webb found no error. The discrepancy survived. And in surviving, it became something far more serious than an embarrassing inconsistency in the data. It became evidence that the standard model of cosmology is missing something fundamental about the nature of the universe itself. Let's be precise about what we mean by the expansion rate of the universe. Edwin Hubble established in 1929 that distant galaxies are moving away from us, and that the farther away a galaxy is, the faster it appears to recede. This was the first direct observational evidence that the universe is expanding. Not that galaxies are moving through space as objects move through air, but that space itself is stretching, the fabric of the cosmos inflating, carrying everything embedded within it farther apart, the same way raisins in a rising loaf of bread move apart from one another, not because they are swimming through the dough, but because the dough between them is expanding. The rate of that expansion is captured in a single number called the Hubble constant. H0 as physicists write it. What it measures in plain terms is this: for every unit of cosmic distance, specifically for every megaparsec, which is roughly 3.26 million light-years, a distance so vast that light travelling since the Big Bang has only crossed about 4 of them, the universe is expanding at a certain speed measured in kilometres per second. The number tells us how fast space itself is growing at any given separation. Getting that number right matters enormously. The Hubble constant determines how old the universe is, how large it is, how it will evolve, and what its ultimate fate will be. A small error in that number compounds across the entire history and future of the cosmos. An accurate measurement is not an academic luxury. It is foundational. The problem is that the universe gives 2 different values, depending on which direction in time you look. The first method looks backward in time as far as physically possible. The cosmic microwave background, the faint glow of heat radiation left over from roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely for the first time, encodes in its temperature variations an extraordinarily precise snapshot of the infant universe. By analysing those patterns with instruments like the European Space Agency's Planck satellite, physicists can reconstruct the physical conditions of the early universe in extraordinary detail, and from those conditions they can calculate how fast the universe must have been expanding, and projecting that expansion forward to today, derive a present-day Hubble constant. The Planck team's measurement comes out at approximately 67.4 kilometers per second per megaparsec. For a sense of scale, that means 2 galaxies separated by 3.26 million light-years are being pushed apart by the expansion of space at about 67 kilometers, roughly 42 miles, every single second. Every second, that distance between them grows by 42 miles, not because either galaxy is moving, but because the space between them is stretching. The second method looks at the nearby universe using objects whose true brightness physicists can calculate independently. Cepheid variable stars are a particular class of star that pulsate, expanding and contracting in a regular rhythm, and whose period of pulsation is directly linked to their intrinsic luminosity. A Cepheid that pulsates once every 30 days is genuinely brighter than one that pulsates every 10 days by a precise and calculable amount. By measuring how long a Cepheid takes to complete one pulsation cycle, astronomers can determine exactly how bright it truly is. By comparing that true brightness to how bright it appears from Earth, they can calculate its exact distance, the same way you can estimate how far away a streetlight is by comparing how bright it looks to you with how bright you know streetlights actually are. Those Cepheid distances anchor a longer chain, allowing astronomers to calibrate the distances to Type 1a supernovae, which are stellar explosions so bright they can be seen across billions of light-years and whose peak luminosity is remarkably consistent. By measuring how fast galaxies hosting those supernovae are receding, the local expansion rate can be computed directly from observation. Adam Rees of Johns Hopkins University, who shared the Nobel Prize in Physics in 2011 for discovering that the expansion of the universe is accelerating, has led this local measurement effort for years under the SH0ES program, which stands for Supernovae H0 for the equation of state. His team's most precise measurements consistently return a Hubble constant of approximately 73 kilometers per second per megaparsec, 67.4 versus 73. That gap, roughly 8%, is not a rounding difference. At the scales involved, 8% represents a profound physical discrepancy. The 2 methods are measuring the same quantity at different cosmic epochs, and the universe is telling them different things. For years, the most straightforward explanation for the discrepancy was a measurement error in the local Cepheid chain. Cepheid measurements from ground-based telescopes, and even from the Hubble Space Telescope, had always been complicated by 2 factors: dust and crowding. Dust, clouds of interstellar gas and particles scattered throughout galaxies, absorbs starlight and makes distant Cepheids appear fainter and redder than they actually are. If dust absorption was being systematically underestimated, the distances calculated from Cepheids would be wrong, and the local Hubble constant would be miscalibrated. Crowding, the problem of stars in distant galaxies being packed so closely together in a telescope image that their light blends, could similarly cause individual Cepheids to appear brighter than they really are by absorbing the light of unresolved neighbouring stars. Again, a systematic error that would corrupt the distance chain. Webb was designed, among other things, to address both of these problems. Its infrared vision cuts through dust far more effectively than visible light observations. Dust is largely transparent to infrared. It absorbs and scatters visible light far more aggressively than it does the longer infrared wavelengths that Webb detects, and Webb's extraordinary angular resolution, its ability to distinguish fine detail, allowed it to resolve individual stars in distant galaxies far more cleanly than any previous instrument, dramatically reducing the confusion from crowding. Rees and his collaborators pointed Webb at galaxies hosting Cepheids that had been previously measured by the Hubble Space Telescope. The expectation, held quietly by many in the field, was that Webb's superior measurements would pull the local value down, closer to 67, and the tension would dissolve. The measurements came back, the dust corrections held, the crowding corrections held, the Cepheid distances held, the local Hubble constant stayed at 73. Rees described the result publicly in terms that were precise and quietly significant. The cosmological model, he suggested, appeared to be incomplete, not wrong in every prediction, not broken, but containing a gap, something missing, that was allowing the early universe and the late universe to behave differently in a way the standard framework had never anticipated. Here is the paradox that sits at the center of this and cannot be easily resolved. The Hubble constant should be a single number. The universe has one expansion rate. Space is either stretching at a particular pace or it is not. The idea that careful measurements using two different methods should produce two meaningfully different values for the same physical quantity is, on its face, incoherent. The same way a reliable thermometer should give the same reading in the same room regardless of whether it is mercury or digital. But both methods are robust, both have been checked exhaustively, both have been corrected for every known systematic error. Multiple independent teams using different telescopes and different calibration approaches have reproduced both values. The Planck team's 67.4 has been confirmed by independent analyses of the microwave background. Rees's 73 has been reproduced independently by the H0 lenses in Cosmo-Grail's Wellspring collaboration, a completely different method using the gravitational lensing of distant quasars. Multiple independent roads lead to the same pair of incompatible values. The statistical significance of this discrepancy has grown as the measurements have improved. By the early 2020s, the tension stood at approximately 5 sigma, meaning the probability that the two measurements are actually consistent with each other, and the gap is just statistical noise, is less than 1 in 3.5 million. That is not a marginal discrepancy. That is a signal. Something is wrong, and the candidates for what is wrong, all of them, require additions or modifications to the standard model. Two broad classes of explanation have emerged, and neither has yet achieved consensus. The first involves dark energy. In the standard model, dark energy is treated as a cosmological constant, a fixed, unchanging property of space itself, present everywhere at the same density, neither increasing nor decreasing as the universe expands. This was Einstein's original concept, which he introduced and later reportedly called his greatest blunder, before its revival when the accelerating expansion of the universe was discovered. A perfectly constant dark energy produces a specific expansion history, which in turn produces a specific relationship between the early universe Hubble constant and the local one. But what if dark energy is not constant? What if it evolved, perhaps stronger in the early universe than today, or weaker, or oscillating? A different dark energy history would alter the expansion rate at intermediate epochs, potentially explaining why the early universe measurement and the local measurement disagree. In 2024, the Dark Energy Spectroscopic Instrument, DESI, published preliminary results from its extraordinary survey of tens of millions of galaxies. The data hinted, cautiously and with appropriate scientific uncertainty, that dark energy might not be constant, that its influence on cosmic expansion may have varied across time. The result was not conclusive. DESI researchers were explicit about that, but the hint pointed in exactly the direction that a varying dark energy explanation for the Hubble tension would predict. The second class of explanation involves modifications to gravity, the possibility that on the very largest cosmic scales, gravity does not quite behave the way Einstein's equations describe. General relativity has been tested with extraordinary precision within our solar system, within binary pulsar systems, and in gravitational wave observations. But those tests occur on scales that are vanishingly small compared to the full extent of the observable universe. Whether gravity behaves identically across a billion light-years of space, as it does across a few light-years, has, in a fundamental sense, never been directly verified. A modified gravity at cosmic scales could alter how structure forms, how expansion proceeds, and, critically, produce different effective expansion rates when measured by early universe methods versus local ones. Neither explanation has yet displaced the standard model. Both require mechanisms that the lambda-CDM framework does not contain, and both, if confirmed, would constitute genuine additions to the map of the cosmos, new ingredients that change not just one prediction, but the entire framework of how the universe evolves. What Webb did to the Hubble tension was decisive in one specific and important sense. It eliminated the last credible instrumental explanation. Before Webb, it was still possible, just barely, to argue that the local Cepheid measurements were systematically off in ways that ground-based observations and even Hubble Space Telescope observations could not detect: dust absorption, imperfectly corrected; crowding, inadequately resolved; a subtle bias in the calibration chain, propagating invisibly through decades of observations. Webb closed all of those doors. Its infrared sensitivity and its resolving power removed the remaining uncertainty from the local measurement to the degree that the measurement error explanation became untenable. What remains is not an instrumental problem. What remains is a physics problem. The universe, when interrogated about its own expansion rate, using the most precise instruments humanity has ever built, gives two different answers. And the gap between those answers has not closed with better data. The gap has sharpened. The Hubble tension, the early galaxy problem, the spin asymmetry, the rotating universe, the black hole cosmology, taken individually, each of these could be dismissed, qualified, subjected to the reasonable skepticism that science demands. But sitting here, having followed this evidence across its full breadth, something else becomes apparent. Every single one of these anomalies points toward the same underlying conclusion. The standard model of cosmology contains at least one missing ingredient, and possibly more than one, that touches the deepest questions about the nature of space, time, dark energy, and the origin of the cosmos. And then there are the little red dots. Scattered throughout Webb's deep field images in nearly every long exposure pointed at the early universe, Webb found objects that no existing category in astrophysics cleanly describes: compact, intensely red, extraordinarily luminous, present at a time when the universe was less than 1 billion years old, and concealing, within their dense and dusty interiors, objects that, if the measurements are right, should not have been able to exist yet. The little red dots may be the strangest thing Webb has found, and what they reveal about the early universe may be the piece that forces the map to be redrawn entirely. They appeared in almost every image, not once, not in a single survey, not in one direction of the sky. Almost everywhere Webb looked when it aimed at the deep, ancient universe, the epoch stretching from 600 million to 1.5 billion years after the Big Bang, the same kind of object kept appearing: small, intensely, stubbornly red, extraordinarily bright for their apparent size, and completely unrecognized. No existing catalogue in astrophysics contained them. No existing model had predicted them. They were not stars. They were not ordinary galaxies. They were not known types of quasars or nebulae or stellar clusters. Astronomers working through Webb's early deep field data gave them an informal name that has since found its way into peer-reviewed literature. Little red dots. The name sounds almost gentle. The objects themselves are anything but. The more carefully scientists studied them, the stranger they became. And what now appears to be lurking inside many of them, hidden behind dense veils of gas and dust, may represent a category of cosmic object that the standard model of galaxy formation has no honest explanation for. To understand why little red dots are so disruptive, we need to first understand what Webb's deep field surveys are actually capturing. When Webb stares at a single small patch of sky, a region that, held at arm's length, might be covered by a grain of sand, and exposes its detectors for hours or even days, the light it collects has travelled distances so vast they become almost abstract. The most distant objects in Webb's deep fields are seen as they existed more than 13 billion years ago. The light entering Webb's mirrors departed those objects when the universe was still in its early youth, when the first generations of stars were only beginning to ignite, when the first proto-galaxies were still assembling from primordial gas, when the cosmos was a place of extraordinary violence and rapid change. At those distances and those early times, the light has been stretched by the universe's expansion until it shifts far into the infrared, wavelengths invisible to human eyes and, critically, invisible to most previous telescopes. Webb was designed for exactly this. Its infrared sensitivity and its position far from Earth's heat-distorting atmosphere allow it to detect objects at redshifts, at cosmic distances, that no prior instrument could access with anything like comparable clarity. And in those newly opened windows of cosmic history, the little red dots appeared, not as rare curiosities at the edge of detectability, as a population, a significant, recurring, pervasive population of objects that nobody had ever catalogued before, because no telescope had ever been able to see them. The redness of these objects was the first puzzle. In astronomy, an object's colour carries information. Redness in a distant object typically signals one of two things. Either the object is very far away, its light shifted toward red wavelengths by the expansion of the universe, or the object is enshrouded in dust, which absorbs blue light preferentially, and allows red and infrared wavelengths to pass through more easily. Think of how sunlight turns orange and red at sunset when it travels through a thick layer of atmosphere. The same principle governs how dust reddens starlight. Most of the little red dots appeared at distances consistent with the first billion years of cosmic history, so some redness was expected from distance alone. But their redness was, in several cases, more extreme than their distance accounted for. The surplus redness pointed at dust, dense, obscuring clouds of it surrounding whatever light source burned inside these objects. Something energetic was happening in their cores, hidden behind a curtain. Their luminosity was the second puzzle. Many little red dots appeared far too bright to be explained as ordinary dwarf galaxies, the small, primitive structures that the standard model expected to dominate this early era. A dwarf galaxy of the size and mass these objects appeared to have should not have been capable of generating this much light. Some additional energy source had to be present. Initial explanations proposed dense stellar clusters, tightly packed aggregations of millions of stars, burning collectively bright enough to account for the observed luminosity. Some researchers suggested unusual stellar populations, with stars weighted toward the massive end of the spectrum and therefore collectively more luminous than typical. Both explanations were reasonable starting points. Both ran into difficulties when the detailed light signatures of these objects were examined. Spectra are astronomy's most powerful diagnostic tool. Every chemical element, when heated to incandescence, emits and absorbs light at specific wavelengths, a unique fingerprint as distinctive as a barcode. By dispersing a distant object's light into its component wavelengths, astronomers can read not just its distance and temperature, but its composition, its motion, and the physical processes occurring within it. When Webb's spectrographic instruments analysed the light from little red dots in detail, they found fingerprints that did not match stellar clusters or dwarf galaxies. They matched active galactic nuclei. An active galactic nucleus is the energetic core of a galaxy, where a supermassive black hole is actively consuming surrounding material, accreting gas and dust at enormous rates, converting a fraction of that in falling matter into radiation so intense it can outshine the entire surrounding galaxy of stars. The spectral signatures of active galactic nuclei are distinctive, broad emission lines from gas moving at extremely high velocities near the central black hole, signatures of highly ionized atoms heated to extreme temperatures, and characteristic ratios between different emission features that reflect the particular physical conditions of an accretion environment, the disk of swirling gas that surrounds and feeds a black hole. Several little red dots showed exactly these signatures, broad emission lines indicating gas velocities of thousands of kilometers per second, thousands of miles per second, moving near their central regions. Gas moving that fast does not do so unless something gravitationally overwhelming is present at the center, something with a mass millions or billions of times that of our Sun, a supermassive black hole. But then came the contradiction that made this genuinely baffling. Active galactic nuclei are, among other things, some of the most powerful X-ray sources in the universe. The accretion disk surrounding a feeding black hole generates X-ray radiation as a natural consequence of the extreme temperatures and energies involved. Wherever astronomers have found the spectral signatures of active galactic nuclei, X-ray emissions have followed reliably, consistently, for decades of observation across thousands of objects. The little red dots showed the spectral signatures. Most showed no X-ray emissions at all. NASA's Chandra X-ray Observatory, the premier space-based X-ray telescope, was pointed at several of these objects specifically to look for the X-ray signal that should, by every established understanding, accompany those spectral features. The search came back largely empty. One little red dot, identified in subsequent observations, did produce a detectable X-ray signal, confirming that at least some of these objects harbour genuinely active black holes, but the majority remained X-ray silent, even as their optical and infrared spectra continued to scream the signature of extreme energetic activity. How do you have the fingerprints of a feeding black hole without the X-ray glow that feeding black holes always produce? One explanation gained traction: the absorbing column. If the central black hole is surrounded by a particularly dense concentration of gas and dust, far denser than typical, then even X-ray radiation, which penetrates most material far more effectively than visible or infrared light, might be absorbed before it can escape. The little red dots may conceal not merely active black holes, but black holes buried so deeply in cocoons of dense matter that only the longest wavelength signals can leak out. The spectral signatures reach us because they originate partly in gas clouds surrounding the innermost regions. The X-rays never escape the interior. This is a coherent explanation. But coherence and proof are not the same thing, and the debate has not been settled. Here is the deepest problem that the little red dots pose. If many of these objects do conceal supermassive black holes, objects containing hundreds of millions or even billions of solar masses, then those black holes existed less than 1 billion years after the Big Bang. In some cases, less than 600 million years after. And the standard model of black hole formation has no comfortable path to producing objects that massive in that amount of time. Black holes grow by accreting surrounding material. The rate at which a black hole can accrete is physically limited by the radiation pressure generated by the infalling gas itself, which pushes outward against the material trying to fall in. This limit, called the Eddington limit, after the British astrophysicist Arthur Eddington, who derived it, defines the maximum rate at which a black hole of a given mass can grow under normal conditions. Growing a black hole from the mass of a collapsing star to billions of solar masses even at the Eddington limit continuously without interruption, requires hundreds of millions to over 1 billion years. Some of the little red dots do not appear to have had that time. The seeds from which these black holes grew would need to have formed extraordinarily early. Primordial black holes, objects that form directly from density fluctuations in the first fractions of a second after the Big Bang, before any stars existed, have been proposed as candidates. A primordial black hole could already possess significant mass before the first star ever ignited, giving it a head start that standard stellar collapse mechanisms cannot replicate. Direct collapse black holes represent a second proposed pathway. In certain conditions in the very early universe, where gas clouds were extraordinarily massive and where the usual fragmentation into smaller clumps and individual stars was suppressed by intense radiation from nearby objects, a cloud might collapse directly into a single massive black hole rather than forming stars first, skipping the stellar phase entirely, going straight from gas cloud to black hole in a single gravitational event. Models suggest these direct collapse objects could form with masses already in the range of 10,000 to 100,000 times the Sun, a far more promising seed mass from which to grow a billion solar mass monster in the available time. Neither primordial black holes nor direct collapse black holes have been directly confirmed by observation. Both remain theoretical frameworks, supported by indirect evidence, and motivated by the need to explain objects that the standard formation pathway cannot account for. The little red dots may be the closest thing to direct observational evidence for one or both of these mechanisms that astronomers have ever encountered. Several things are now reasonably established. Little red dots form a genuine population of previously unknown objects in the early universe. Webb did not stumble on one or two outliers. It found them repeatedly in multiple surveys at consistent redshifts with recurring spectral characteristics. The spectral signatures of at least a subset resemble active galactic nuclei powered by supermassive black holes. At least one has been confirmed as an X-ray source, establishing a direct physical link to black hole activity. And the masses inferred from the spectral line widths, if interpreted straightforwardly, imply black holes that exceeded the growth rates permitted by standard models. What remains unresolved is almost everything else. The true nature of the majority of little red dots is still contested. Some may indeed be super Eddington accretors, black holes consuming material at rates above the theoretical limit, a possibility that some models allow under extreme early universe conditions. Some may involve a combination of stellar light and nuclear activity, whose relative contributions are not yet cleanly separated by available data. Some may be explained by exotic stellar populations that produce AGN-like spectra through mechanisms not yet fully understood. The debate is active, the data are still accumulating, and no consensus has crystallized. What is not debatable is that these objects should not dominate the early universe if the standard model of black hole formation is correct. Their abundance, the sheer number of them appearing in Webb surveys across the sky, already implies that the early universe was producing whatever they are at a rate that exceeds predictions by a significant factor. One team of researchers, working through the implications of Webb's deep field counts, estimated that little red dots may represent some of the most common luminous objects in the universe at their epoch, more common than known quasars of comparable luminosity, more common than the models anticipated by orders of magnitude. That is not a small discrepancy to absorb. The little red dots sit at the intersection of nearly every crisis the Webb data has produced. Early black holes that grew too fast, connecting to the early galaxy problem. Objects whose spectral signatures suggest one physical reality, while their X-ray silence implies another, echoing the pattern of anomalies that refuse to fit neatly into existing frameworks. Black holes that may have predated the galaxies they should have formed inside, a reversal of the sequence the standard model demands, and above all a population of objects so numerous and so energetically extreme in the first billion years of cosmic history that their presence alone strains the boundaries of what current astrophysics says was possible. Taken together, The oversized ancient galaxies, the spin asymmetry, the Hubble tension, the black hole cosmology, and now the little red dots. The picture that has emerged from Webb is not one of a model with minor gaps. The picture is of a cosmos that formed more structure, more complexity, more organized asymmetry, and more massive objects, more quickly than any version of the standard model comfortably permits. That accumulation of strain has a name in the history of science. Scientific revolutions do not announce themselves with a single overturning discovery. They begin exactly like this, with anomalies stacking quietly, each one explicable in isolation, until the weight of them together becomes too great for the existing framework to bear. We may be living through that moment right now. Not yet at the collapse of the old framework. Science demands more before that verdict is returned. But at the point where the question must be asked honestly, without flinching, is cosmology entering a new scientific revolution? Scientific revolutions do not announce themselves. That is the thing history keeps teaching us, and we keep forgetting. When Copernicus placed the Sun at the center of the solar system, his contemporaries did not immediately recognize that the architecture of reality had been redrawn. When Einstein published his theory of general relativity in 1915, most physicists needed years to absorb what it meant. When Edwin Hubble confirmed the existence of other galaxies in 1924, the full consequences of that discovery, that the universe was billions of times larger than anyone had imagined, took a generation to settle into scientific culture as a lived, understood reality. The pattern is consistent, a framework that has explained everything, anomalies that begin appearing at the edges, pressure building slowly, quietly, without dramatic announcement, and then a tipping point, the moment when the accumulated weight of unexplained observations can no longer be absorbed by the old map, and the scientific community begins building a new one. We may be standing at exactly that moment right now, or we may not be, and the honest uncertainty of that sentence, the genuine inability to say which, is itself one of the most remarkable things about the position cosmology now occupies. Before we can understand what is at stake, we need to hold something clearly in mind. The standard model of cosmology, the lambda-CDM framework, built across decades of observation and calculation, is not a failed theory. It is not even a struggling one in most of the domains where it has been tested. The lambda-CDM model predicted the large-scale structure of the universe, the vast cosmic web of filaments, nodes, and voids that spans billions of light years, and observations confirmed it in extraordinary detail. The model predicted the precise pattern of temperature fluctuations in the cosmic microwave background, and satellite measurements matched those predictions to within fractions of a percent. The model predicted how galaxy clusters should distribute themselves across cosmic time, and surveys confirm the predicted distribution. The model predicted the acoustic oscillations, the subtle, regular patterns in the density of matter, imprinted by sound waves in the early universe, that should appear in the large-scale distribution of galaxies, and spectroscopic surveys found them exactly where the model said they would be. On the largest scales and across the broadest range of observations, the standard model remains one of the most successful scientific frameworks in history. That is not a qualification offered to soften what comes next. That is a fact that must be held alongside what comes next. Because a scientific revolution, when it arrives, does not invalidate everything the previous framework got right. General relativity did not erase Newtonian mechanics. Newtonian mechanics still land spacecraft on the moon. What general relativity did was extend the map into regions where Newton's equations failed, regions of extreme gravity, extreme speed, extreme curvature. The new framework contained the old one as a special case, applicable within its original domain. Whatever is coming in cosmology will almost certainly do the same. The new map will explain what the old one explained, and it will extend into the regions Webb has now opened, the regions where the old map currently says things that the universe quietly, persistently refuses to confirm. Let's step back and look at what has accumulated. Early galaxies that grew too massive, too fast, containing too many stellar generations for the time available. Requiring star formation efficiencies the physics of gas cloud collapse does not permit. A galaxy spin asymmetry, two-thirds spinning one way across Webb's deep fields, that defies the statistical isotropy the Standard Model demands and connects to the axis of evil anomaly in the cosmic microwave background and to dark flow measurements pointing in approximately the same direction. A Hubble tension, a persistent, statistically decisive discrepancy between the expansion rate measured from the early universe and the expansion rate measured locally, that survived Webb's most precise corrections and that now stands at a significance level where random chance is an essentially untenable explanation. Little red dots, a pervasive, previously unknown population of early universe objects harboring black holes that, by every standard formation mechanism, should not yet exist. Each of these, individually, could be an anomaly awaiting a conventional explanation. Science is full of anomalies. Most resolve. Most turn out, with better data or better models, to have explanations within the existing framework. But here is the thing most people do not immediately appreciate. These anomalies are not pointing in different directions. They are not scattering randomly, the way errors and coincidences scatter. Several of them appear to be connected, pointing at the same underlying gap in the framework. The spin asymmetry connects to the rotating universe hypothesis. The rotating universe connects to the need for an external reference, which connects to the multiverse. The black hole cosmology framework connects to the spin asymmetry, to the origin of the arrow of time, and to the question of what conditions preceded the Big Bang. The oversized early galaxies connect to the little red dots, and both connect to the possibility that the early universe harbored massive black holes before stars had time to produce them through standard pathways. This is not a collection of isolated puzzles. This looks increasingly like a collection of symptoms, and in the background, persistent, unresolved, growing sharper with every new data set, the Hubble tension continues to suggest that the expansion history of the universe does not follow the trajectory that a standard Big Bang, governed by a constant dark energy, predicts. The scientific community's response has been exactly what it should be: expanded investigation into frameworks that would previously have remained on the theoretical periphery. Wave dark matter, also called fuzzy dark matter, has attracted renewed attention in recent years. Standard cold, dark matter models treat dark matter particles as effectively point-like and cold, slow-moving, with negligible quantum effects at galaxy scales. Wave dark matter, by contrast, proposes that dark matter consists of extremely light particles whose quantum wave nature operates on the scales of dwarf galaxies, where standard cold, dark matter models have consistently produced predictions that clash with observation. In wave dark matter models, the quantum interference of dark matter waves suppresses the formation of small structures and creates specific density profiles in galactic centers that match some anomalous observations more accurately than standard models. Webb's high-resolution imaging of faint, distant galaxies has provided new tests of dark matter's behavior at small scales, and several research teams have found that wave dark matter matches the shapes and density profiles of certain early elongated galactic structures more successfully than cold dark matter does. Some researchers have revisited the idea that the fundamental constants of nature, the speed of light, the strength of gravity, the charge of the electron, may not be truly constant across cosmic time or across different regions of space. This idea, known as varying constants cosmology, was explored in the 1990s and early 2000s, faced significant theoretical challenges, and was largely set aside. Webb's ability to probe extreme redshifts to examine the physics of the universe at epochs when conditions were radically different from today has given observers new tools to test whether the atomic physics governing spectral line positions behaved identically in the deep past as it does today. The tests so far have not definitively confirmed variation, but they have constrained it, and in constraining it, have kept the question alive rather than closing it. Proposals for a slightly older universe, where the age is revised upward by enough to provide additional time for early structure to form, continue to circulate in the literature despite strong mainstream resistance. The evidence for the universe's current accepted age of 13.8 billion years is robust and multi-layered, resting on several independent measurement techniques that converge tightly. Significantly revising that figure upward would require not one but several of those independent measurements to be systematically wrong simultaneously. Most cosmologists consider that improbable, but the early galaxy problem has been severe enough that some researchers have argued the age question deserves re-examination with fresh eyes. Here is the position cosmology now occupies, stated as plainly as possible. The Standard Model explains the large-scale structure of the universe with extraordinary precision. Webb has confirmed several of its predictions in regions of cosmic history no instrument had previously accessed, and Webb has also delivered a set of observations, not one, not two, but a growing catalogue, that the Standard Model cannot explain without invoking mechanisms it does not currently contain. Star formation efficiencies above physical limits, expansion rates that disagree with themselves, black holes that predate the timelines their own formation processes require, a statistical directionality embedded in galaxy, spins across cosmic scales, a population of early universe objects with no recognized classification. The Standard Model is not broken, but the Standard Model is not complete. The map is accurate within the territory it was built to describe. Webb has revealed that the territory is larger than the map. Regions exist early enough, dense enough, extreme enough, where the map's contour lines simply run out, replaced by blankness that honest cartographers must label with a phrase science rarely gets to use with genuine humility. Here, we do not yet know. The history of science offers a useful guide here. Thomas Kuhn, the philosopher and historian of science, described in his 1962 work, The Structure of Scientific Revolutions, how paradigm shifts actually occur. Normal science, he argued, operates within an accepted framework, accumulating results, filling in details, extending the map. Then anomalies appear. At first, they are treated as puzzles to be solved within the existing framework. Explanations are proposed, some succeed, but some anomalies resist all conventional resolution. They accumulate, scientists feel increasing discomfort, and eventually a new framework emerges that redraws the map at a deeper level, not by discarding the old framework, but by revealing it to be a special case of something more comprehensive. Kuhn called this a paradigm shift, and the signature of an approaching one is precisely the pattern we now see. Multiple simultaneous tensions, each individually explicable in isolation, collectively too coherent and too persistent to dissolve without new physics. Are we there? The honest answer, the one that the data currently supports without overclaiming, is this: we are not yet certain. The anomalies are real, the tensions are real, the statistical significance is in several cases extremely high, but science demands more than high statistical significance before dismantling a framework as successful as lambda CDM. It demands a better framework to replace it, one that not only explains the anomalies, but preserves and extends everything the old framework correctly predicted. That framework has not yet arrived. What has arrived is the clearest indication in decades that it is needed. Pause for a moment. Feel the weight of the screen or the phone in your hands. The room around you, quiet or not, is filled with light, with photons bouncing off walls and objects at the speed of 300,000 kilometers, roughly 186,000 miles per second. The air you just breathed contains atoms forged inside stars that died before the sun was born. The chair or surface beneath you is the product of nearly 13.8 billion years of cosmic history, hydrogen forged in the first minutes after the Big Bang, assembled into stars, into planets, into molecules, into the structure your weight rests on right now. All of that, all of it, is what the map describes. And the map is real, and the map is powerful, and the map has carried human understanding farther than anyone who drew the first star charts could have imagined, and the map is incomplete, and a telescope named Webb, orbiting 1.5 million kilometers, nearly 1 million miles, from Earth at the gravitational balance point called L2, is sending back images that the map makers never drew, images of a territory that extends further and reaches deeper and conceals more than the most ambitious cartographers of the 20th century believed possible. Science does not break when it finds what it cannot explain. That is not a failure of science. That is science functioning exactly as it was designed to function. The goal was never to produce a final map. The goal was always to produce a better one. Every measurement that contradicts the model is a gift. Every anomaly that survives verification is a gift. Every crisis that forces a community of careful, skeptical, brilliant people to reconsider their most deeply held assumptions is a gift, not to the institutions or the careers or the theories, but to the actual project of understanding what the universe is. Webb's deepest images are gifts of exactly this kind: uncomfortable, destabilizing, and irreplaceable. Cosmology now stands at the edge of something, whether that something is a refinement of the existing framework or a genuine paradigm shift. A new map large enough to contain both the territory we thought we knew and the territory Webb has opened remains to be seen. The data continue to arrive. The surveys continue to expand. The Euclid Space Telescope is mapping the large-scale structure of the universe in unprecedented detail. The Vera C. Rubin Observatory will catalogue tens of billions of stars and galaxies over its operational lifetime. The next generation of instruments is already being planned. The universe has more to say, and we have built the tools to listen. You have followed this a long way, from the first images that did not match the map, through galaxies that grew too fast and black holes that arrived too early, through the geometry of a possibly rotating cosmos, and the quiet persistence of a tension in the universe's own expansion rate, through objects too strange to name and anomalies too coherent to dismiss. This was not a simple story. It was not supposed to be. The universe is not simple, and neither, it turns out, are we, these small, warm beings on a pale planet around an ordinary star, somehow capable of building instruments that reach 13 billion light-years into the past, and feeling genuinely unsettled by what we find there. That capacity to be unsettled, to let a data point disturb a cherished belief, to build a new question from the ruins of a confident answer, is the thing that makes science something more than a body of knowledge. It makes it a practice, a living thing. The map we drew was remarkable. The territory Webb is revealing is more remarkable still. And somewhere at the edge of what we can see, where the deep fields run out and the instruments reach their limits, the universe continues, as it always has, indifferent to our theories, faithful only to its own nature, waiting to be understood. We began tonight with a map, a century of careful, beautiful, precise scientific work, drawn into a portrait of how the cosmos began and grew and spread across 13.8 billion years of time. A map we thought was nearly finished. Webb did not tear the map. It revealed the map for what it always secretly was, not a portrait of the whole territory, but a portrait of the territory we could reach, beyond the edges of that map, past the confident contour lines and the labelled epochs. The universe continued in ways we had not drawn, not because we drew it wrong, because the territory is larger than any map built so far has been designed to hold. The next map will be bigger. It will take everything the old one got right and extend it into the regions where the old one went quiet. And whoever draws it, the physicists and cosmologists and instrument builders of the coming decades, will stand on the work of everyone who came before them, including the teams who built and operate the telescope that forced the question open. The deeper Webb looks, the less complete reality appears. And the less complete reality appears, the closer we are getting to what it actually is. Here is what strikes me most quietly about all of this. Every human life is also a map drawn in real time, a portrait of what we think reality is, built from everything we have experienced, everything we have understood, everything we have had the courage to question, and every life, if lived with honesty, eventually reaches the edge of its own map, the place where the confident lines run out, where the territory continues in directions we did not draw. That edge is not a failure. That edge is where everything real begins. You sat with that tonight, with the unknown, with the genuinely unresolved, and you did not look away. Thank you for traveling this far. If something in this moved you, if the universe feels stranger and more alive than it did before, please subscribe. The map is unfinished for the universe, for all of us, and that, quietly, is the most hopeful thing there is.